Now we would like to look at the Laplace transform and system properties like stability and causality and invertibility in terms of the transform and its region of convergence. So we'd like to be able to characterize both stability and causality in terms of the region of convergence. We'd like to find all time domain signals with a given transform, and we'd like to determine if causal and stable inverses exist for a given transform. Given a Laplace transform h of s, which is a rational transform with ROC R of h, we can try to figure out what certain system properties are. Now remember, if we have a rational transform, we don't allow delay, so there's no e to the minus s tau or something like that term in the Laplace transform. So that is, if h of s is a causal system, remember this means that h of t is right-sided. And we know that for right-sided systems, R of h goes to the right, goes off to infinity. And so in particular, since the ROC cannot contain any poles, it goes from the rightmost pole to infinity. If h of s is anti-causal, then we get the opposite, that the region of convergence goes from minus infinity to the leftmost pole. So those are two conditions, and we'll see some pictures that make it a little bit clearer. If our system is stable, it's stable if and only if the region of convergence contains the imaginary axis. So in particular, causal plus stable means that the RH goes from the rightmost pole to infinity, and the ROC must contain the imaginary axis. So therefore, all poles are in the left half plane. And sometimes you hear this as a condition for causality and stability, or it's a desirable property for Laplace transforms is to have all the poles in the left half plane, and that's where this comes from. And finally, we can invert a system if we can essentially take g of s is equal to 1 over h of s. If we can find an ROC for this g of s such that the intersection between RH and RG isn't empty, that is, when we compose them together, we still have some region of convergence, then we can say the system is invertible. And so we can use these properties, of course, also to find a time domain signal with the given Laplace transform. Given the ROC, we can figure out what is the corresponding time domain signal has to be. So just a reminder, multiple signals can have the same Laplace transform with different ROCs, right? So if we have this signal y of s, which has got a 0 at 1 and poles at -3 and -1, we can draw the pole 0 diagram, and we can identify three different ROCs. We can have one going from this pole at -1 off to infinity, and we can see that that means that that's a right-sided signal. We have one that goes from the leftmost pole -3 back to minus infinity, and that's a left-sided signal. And we have one that's sandwiched between the two poles, and that's going to correspond to a two-sided signal. And so just looking at the partial fraction expansion over here, we can see we can pick inverse transforms for each of these two terms to get a right-sided signal here, a left-sided signal here, and a two-sided signal here, right? So we have the u of t and a u of t, so that's right-sided, u of minus t, so that's left-sided, and then finally we have a mix between a u of t and a u of minus t, so that's going to give us a two-sided signal. So remember the most important fact, that convolution in the time domain is multiplication in the Laplace domain. So we can sort of find the same y of s by, say, breaking it apart into an x of s and an h of s, just for hypothetical. So we can put the 0 and the pole at -1 into x of s, and then we can put the pole at -3 into h of s, and so we'll get these two choices for h of x. We'll get these x of s and h of s, and now the question is, why do we have only three regions of convergence? Don't I have two choices for x and two choices for h? Right, so I have two different x of t signals with the same x of s and two different h of t signals with the same h of s, and the only difference is the region of convergence for each. So I have two choices for x of t. I have a right-sided choice and a left-sided choice, And similarly, I have a right-sided choice and a left-sided choice for h of t. Now, the thing is, we need to make sure that the ROC it contains the intersection of Rx and Rh, or in fact, if there's no pole zero cancellation, there's no pole zero cancellation here, then it's going to be equal to the intersection of Rx and Rh. So, if we choose a right-sided x of t and a left-sided h of t, then it turns out we're going to get no intersection. So there's no region of convergence here. So this pairing doesn't yield an output. Whereas the others, we can get a right-sided, a two-sided, and a left-sided, are signals from the previous slide if we do the corresponding convolution. Right, so in order for y of t to exist, the intersection of the regions of convergence cannot be empty. So let's find all the impulse responses which can lead to a given transform, right? So using our knowledge of right and left-sidedness, or causality, anti-causality, and so on, and stability. Let's see if we can understand this. So here's an impulse. Here's a system h of s, and it's got three poles at -2, -6, and -4, and a 0 at -5. So if you draw out the pole zero diagram, you can draw out the pole zero diagram. Here's a 0 at -5, and then there's one at a pole at -2, -4, and -6. And you can see that we're going to have a couple of different regions of convergence. We're going to have one that looks like this. We're going to have one that is sandwiched between the two poles that looks like this. And we have one that looks like this, that's sandwiched between those two poles. And finally, we have one which is going to go from -infinity to the leftmost pole. Right? And these four different ROCs correspond to these four different choices of the region of convergence. And then we can look at this region of convergence and we can say, okay, does it contain the imaginary axis? Is it go from the rightmost or leftmost pole off to infinity or -infinity? And so we can see that this first one, this first ROC goes from -infinity to -6, and so it's left-sided. ROC doesn't contain the imaginary axis, so it's unstable. The one from -6 to -4 is two-sided because it doesn't go off to ±infinity. The ROC is bounded between two poles, so it's two-sided, but it's still unstable. We have another one that's two-sided, unstable from -4 to 2. And then we have finally the one that goes from the rightmost pole at -2 off to infinity. That's right-sided and stable. Right, so there are four different h of t's with four different ROCs, which correspond, or which give the same h of s, but with different ROCs. So here's the diagram that I drew on the previous slide, but kind of written out here. We can see these four different ROCs, and remember we have stability corresponds to whether the imaginary axis here. So this one over here is stable, and we look to see whether it goes from the rightmost pole. So this one is off to infinity. So this is causal. This is anti-causal because it goes from the left -infinity to the leftmost pole. And so we have no stability here, unstable here, two-sided, and unstable two-sided here as well. So now how do we find the time domain signals, right? So we've identified the ROCs. We're like, okay, so there's got to be four signals out there. How do I find them? Well, first off, we need to do partial fraction expansion on h. So just doing our partial fraction expansion, we get three different coefficients here, and so we get this partial fraction expansion of h of s. So this should be fairly standard. You can maybe hit pause and go through the derivation yourself to make sure there are no algebra errors. But the point is that for each of the corresponding ROCs, we have four of them. We essentially have to choose which inverse, left or right-sided, time domain signal to choose for each of these three terms. Right, and so basically we want to make sure that the choices that we make, when we make the choices for each of these three terms, when we intersect the ROCs for each of the three terms, we get the total ROC for h of s that we identified earlier. So that is, we pick an ROC for h, then we pick three signals, and we check to see is the intersection of the ROC of say, let's call this R1, R2, and R3. We want to make sure that the intersection of R1, R2, R3 is going to be the ROC that we chose for H. Right, and so here again are our four different ROCs, and here are the four different time domain signals. So remember, so this one, remember, is going to be left-sided. So I have to choose the left-sided inverse for all three terms if I want the overall signal impulse response to be left-sided. So here we chose all three left-sided terms. Let's do the other one, which is easier, which is the right-sided one. Right, so if this is right-sided, then I choose the right-sided term inverse Laplace transform for each of those three terms. Now what about the ones in the middle with the two-sided Laplace transforms? Well, so if we look at the one that goes from -6 to -4, what are we saying here? Well, we're saying we have poles at 2, -4, and -6. So if I intersect the region of convergence, so here's the region of convergence for the e to the minus e to the minus 2tu of minus t, and here's the region of convergence for e to the minus 4t minus e to the 4 minus t e to the minus e to the minus 4t u of minus t, and then we have to take the one corresponding to the right-sided version of e to the minus 6t. So this is e to the minus 6t u of t. And so the intersection of those three regions of convergence gives us exactly this region of convergence here. Right? So we're going to choose the left-sided version of the -4 and the -2, and the right-sided version of the -6. And similarly over here, we're going to choose for this last region of convergence, we're going to choose the right-sided versions of 4 and 6, and then the left-sided version of 2, and we'll get the intersection that corresponds to this. So the last thing we can do is we can see if a given system has a stable causal inverse. So here's an H of S. It's got two zeros and a pole. And we give the region of convergence. It's this one is causal, so it's got R of the real part of S has to be greater than -3. It's a right half plane. So what can we do? We can take the algebraic inverse. So we just take 1 over H of S. Right, so 1 over H of S equals G of S. We can do partial fraction expansion on this to get two different terms. And we can see there are three different possible ROCs for this because there are two poles, one at -1 and one at -2. So we can go from -infinity to -2, -2 to -1, or -1 off to infinity. And this last one, this last one here, this contains the imaginary axis, so it's stable. And it's a right half plane, so it's causal. So we have a last one which is stable and causal, and we look at the intersection between the ROCs between these two terms, and we're going to get that the ROC is going to be the real part of S is greater than -1, and we're going to choose both right-sided. We're going to choose both the right-sided versions of the two terms corresponding in the partial fraction expansion. Right, so this is a stable causal inverse for this system up here. So the question is now, let's just flip the sign in the numerator flip the sign of the 0. So we now have S of -3. And we're going to choose this region of convergence. So again, we take G of S is equal to 1 over H of S. So we have S plus 1 on S plus 2 over S minus 3, S squared, which we expand out, and then we have to do, here we have to do long division instead of partial fraction expansion. And we get out this, this sort of expression here. It was just doing the algebra. And we can see already that we're in trouble because we have this S minus 3, that's a pole at plus 3. So we have a pole in the right half plane. So remember, it had a stable and causal inverse. We need all the poles in the left half plane. Here we have a pole in the right half plane. So we're going to be sunk at least on getting both of them. But since it's only got one pole, let's look. We got two different ROCs, greater than 3 and less than 3. And so we can see if we want to intersect R of h, so we intersect R of h with each of these two terms here, we get we get minus 1 is less than real part of s is less than 3. So this is a stable because it contains the imaginary axis, but it's a two-sided signal because it's sandwiched between two different poles, if you like. It doesn't go off to infinity or minus infinity. And the other option is to choose the real part of s is greater than 3, but that is definitely unstable because it doesn't contain the imaginary axis, but it is right-sided. So we can get a causal unstable inverse, or we can get a two-sided but stable inverse. So the answer is no, we don't have a stable and causal inverse, right? And causal. But we can either a stable or a causal inverse. So just as always, it helps to really try some examples yourself. You can take either the examples that we did in this presentation and like tweak the numbers a little bit and do it yourself, or here are some other examples you can try to determine if the systems are causal or anti-causal or stable or unstable, and then see if you can invert them. So, and whether the inverses are causal or stable, or whether you can have a causal and stable inverse.